So it's my great pleasure to introduce our speaker today, Dr. Duan from the University of Florida. So Leo is currently an assistant professor at the University of Florida, and he has joined positions at Brain Institute and the Informatics Institute at the University of Florida. And then he has done many interesting works. His research spans many interesting fields, including Bayesian statistics, optimization, graph theory, and combinatorics. And I guess today he is going to talk about how to build a Bayesian generator model for spectral clustering using spanning formats.
Yeah.
And welcome, Leo.
All right. All right. Thank you. Can you hear me? Okay. Let me move this up a little bit. All right. All right. Thank you, Chan, for the introduction, and thank you so much for the invitation. And it's really exciting for me to visit this department. This department has a huge name, and I'm really flattered that being able to stand here and share with you about our recent discovery. So in my opinion, we consider this as a huge discovery because I consider this as an analogy to the relationship as a Gaussian mixture model to k-means, and we figured that this could be like a generative model for the spectral clustering algorithm, which is like really popular nowadays in the machine learning literature. This is a joint work with my colleague Akarprabha Roy from the University of Florida Biostat department, and so I'm just gonna jump right in and just to do some literature review, and then I will tell you about something about our model, and then I will tell you some nuance between our model and the existing model, because as you probably know, that the spanning tree and spanning forest has been there for at least 50 years, and I'm going to show you what distinguishes our method by taking a Bayesian approach compared to, let's say, the minimum spanning tree approach. Okay, and then I'm going to tell you about computation. Then I think what's interesting is that I'm going to show you that we found that there is an implicit connection in terms of the eigenvectors that we found that almost identical eigenvectors there. And then I'm going to tell you about some uncertainty quantification. I think that's what's really excited me the most is that we found out that we apply this method to some side extension. We found that it worked amazingly well on some real world high dimensional data, such as clustering phase photos. Okay, so first of all, let me tell you quickly about some existing literature. Of course, there is a huge literature on clustering method, including Bayesian approach. But just to introduce some notations, clustering method is basically conducts the task of partitioning the data denoted by y1 to yn into disjoint groups that I call this partition using this V here. I guess I have a pointer that I can use. Oh, you know what? Let me just use the mouse because it's really tall there. Okay, so let me denote each partition by V, and the task of clustering is very important for characterizing and also reducing the heterogeneity of the data. And just very roughly, we can categorize them into two categories. For example, there has been a lot of deterministic algorithms. Some of them they work amazingly well, such as k-means or this thing called DB scan. It actually won something called Test of Time award at some machine learning conference, and it worked really well for its flexibility. On the other hand, we have this thing in the statistical literature that we call a model-based clustering. Okay, but for today's talk, I would like to add an attribute to it. I call it mixture model-based clustering. So because of the essential idea is that if we assign a mixture likelihood, that we assume that the parameter may follow a discrete distribution, and then each data points will take a value from this discrete distribution, and then we have and then if you combine those two pieces together, you get a mixture likelihood. Okay, so this mixture model-based clustering framework is extremely popular in both the statistics and the machine learning primarily for two reasons. First of all, compared to the deterministic algorithms such as dbScan or k-means, it just automatically gives us uncertainty quantification, and it is a very principled approach because we can quantify the uncertainty using the posterior probability. For example, there could be like one point of interest is a clustering assignments, and the probability that characterizes the uncertainty of the probability, the cluster assignment. And more interestingly, you could do inference on things, for example, like the distance between two centers of the cluster, et cetera, et cetera. And of course, the number of a cluster is a huge topic that generated a lot of recent work lately. And another aspect, this is something that I feel that don't get to talk very much, is that if you taking a model-based approach, actually it just makes things easier to do model-based extension. For example, like Peter Mueller has done a lot of work on using covariates to do like a more informative clustering, like a covariate dependent clustering. And of course, we've seen a lot of interesting application. For example, in natural language processing, people do topic modeling by building model within this model-based clustering framework. Okay, and on the other hand, the downside of the classical model-based clustering framework is that it requires to have a correct model specification. So this issue has been discovered recently, that if you are thinking about assigning a mixture component distribution, and then if somehow this component distribution is just slightly misspecified. For example, if you have a data generated, if you have generated from a mixture of skew normal instead of normal, and then you apply, let's say, dirichlet process mixture of normal, then you'll see that you get an explosion of tiny little clusters. And this is not an issue with the dirichlet process itself. For example, like recently, Diana Kai et al., they also find that if you use a mixture of finite mixture model, it still does not still cannot effectively control the number of clusters. Okay, and the second issue is that this method works pretty well in low dimensional space. However, when it comes to high dimensional, we have parameters that each component parameters that lives in high dimensional space. Then we will encounter this curse of dimensionality, where you will see that the number of cluster will grow unbounded if you don't impose any upper bound on number of components, number of clusters. And recently, we also found that even if we put a cap on the number of components, the existing algorithms, the MC or EM algorithm, will tend to get stuck at the initial value. So, which is really a serious issue that needs to be addressed. And further, at the end of the day, if you think about it and reflect, like it's for some high dimensional data, it's just tremendously difficult to model everything right. For example, I just put this photos here because if you think about clustering breeds of dog, it's very hard to say. It's just implausible. It's just implausible to say that like maybe this dog is the average of this dog and this dog, right? It just doesn't work that way. Perhaps you need to spend all that effort to come up with some like dog manifold, and so that you can make things work. But it's just really hard. It's a really hard problem. Okay. So of course, this problem has been realized by a lot of our peers. And there's a lot of recent literature in the Bayesian non-parametric literature trying to solve this problem. I'd like to mention that that we did some work about 2 years ago, thinking about using the pairwise distance as an insufficient statistic, and then we just model that insufficient statistic, and we get some robustness for clustering. And I also like to highlight like the work done by Hui and San and Bani Malik on the contiguous partitioning. Okay. Okay. So let me talk about my proposal today. Okay. So I will focus on this thing that I call graphical model-based clustering. Okay. So the gist of the idea is that if we think about assigning a likelihood based on a generative graph that I call G, for example, you consider it as a DAG, and then we make this generative graph separable into k many different parts. So each part here characterizes the distribution for the generative process for each cluster. Okay, and then we're going to assign G and then estimate the partition. Okay, so perhaps the simplest case is consider this G as a spanning forest. Okay, so what do I mean by spanning forest? Well, spanning forest is a disjoint union of k many spanning tree. And if you think about spanning tree, basically it's about you know, if you look at one of those three pictures, you can think about like I have many dots in one cluster, and I want to connect this through a graph. Okay, but I want to use the smallest graph while still connect everybody inside of the cluster. Okay, so as a result, you will get nk many nodes, but only nk minus 1 many edges. So this is really a minimalist graph, a tree graph that connects everybody in a cluster. Okay, and what we do next is that in order to prescribe a generative model, we equipped each tree with a root node associated with a probability kernel, and then we will assign a conditional distribution that describe the relationship from one data point to the next. Okay, so we call the first node that we pick in each cluster as a root, and the other, like those dependent distribution, we call it as a leaf. Okay, so of course this likelihood itself is not new. As I mentioned, like the spanning tree idea originated like back into in the 50s, and the mixture of trees. This idea has been explored by Melina and Jordan in 2000, and there is an algorithm called the single linkage, and Hartigan has discovered that the single linkage algorithm is exactly the same as the process of finding the minimum spanning tree, meaning that you want to find a spanning tree that minimizes the total pairwise distance on this tree, and then you just cut the longest few edges so that you get a spanning forest. Okay, so as you can see, this likelihood is almost identical to the existing work. However, a fundamental difference here is that if we take a step back and think about it, our goal of inference is to do clustering. Okay, so that means you may not care about the graph itself. Okay, instead, what we care about is the subset of the parameter of the graph. So we care about the node partition, but we may not care about where the root is, what are the configuration of the edges. Okay, so that means we can take a drastically different approach. That is, if we just treat the node partition as a key parameter of interest, but the other parameter, like the graph, given this node partition, we treat it as a nuisance parameters, or in Bayesian terms, we call them latent variables of no interest. And then we will marginalize them out to get the marginal posterior. Okay, and then we are going to use that to estimate the clustering probability. So I will show you that this will lead to a very different behavior when it comes to clustering, for example, compared to the MST cut algorithm. Okay, so to finish the model specification, you can pick any distribution that is appropriate for your data, but just for generality, I mean, for general practice, we found out that these choices seems to work very well empirically, at least for continuous data. That is, for the leaf distribution, we can pick a Gaussian distribution, and because of the heavy concentration, and for the root distribution, we pick a Cauchy because it's relatively diffuse. Okay, and okay, so this is where things get quite interesting. Okay, that is, if we take a linear approach, we can regularize our model using prior. And as you can see, the task boils down to how do we assign a proper prior for this spanning forest. Okay, so if you take a hierarchical top-down approach, you can think about the following step. Okay, so we will first assign a prior on the number of trees, and then we assign a prior on the partition, and conditional on those two items, we assign prior on the edges, and then perhaps we can pick one of them as a root node. Okay, as you can see, in this case, we can categorize them as two parts. One of them is the prior on the partition, and the other part is like the graph given the partition. Okay, so you can see that since we have no preference on these parts, so in this study we can just use a discrete uniform, and which will lead to this multiplicity. Okay, it's nk to the nk minus 1. Okay, so I think what's quite interesting is that this has an intimate connection to the existing Bayesian parametric literature, namely the Chinese restaurant process or the polyarm process. Okay, because if you look at if you think about the equivalent generative process, you will get to see this prediction rule. That is, if you think about like we generate this graph by adding one node at a time, what we do is that we can start with the first edge. We have to start with the first node, 0, and then we may have an edge, 0, 1. And then each time we add in a new edge, there is a chance that we connect it to an existing tree, or we just start with a new, we just start a new tree by adding a root. Okay, so this thing will look very familiar with the classic polyarm process, because if you think about it, if you replace this red part with a point mass, then it is exactly the polar process. Okay. However, as you can see, this will give you a continuous distribution as opposed to a discrete, almost surely distribution. Okay. So so as you can see, this is a generalization, and we call it the forest process. And we can certainly just use the canonical parameterization from the restaurant process for those predictive probabilities. And the interpretation is quite interesting, because if you think about restaurant process, it's about like arranging new customers to different tables. You can either add a table or put the customers on to a particular existing table, right? And here the difference is that we still just assign customer to an existing table and a new table, but once we put that particular person at the existing table, this person will only talk to one person that arrived early. Okay, so that is basically a visualization, like the intuitive explanation of this forest process. Okay, however, what's quite surprising is that this will lead to a very different prior once we marginalize out the order of I and the customer ID. Okay, so you can say that on the marginal distribution of this G, we get this term that we are familiar with. Okay, the partition function of corresponding to of a restaurant process. Okay, but in addition, we get this part, which is inverse of a huge term, that is nk to the negative nk minus 1. Okay, so we may wonder, where does this term come from? Okay, so in fact, we actually spend a lot of time in trying to justify this term, and later we found out that this term is actually due to the graph of multiplicity. Okay, and the reason that we see this multiplicity term, inverse of multiplicity term here, is and not in the model, let's say not in the standard restaurant process, is because if you think about it, you're assigning a mixture. If you're thinking about if you think about the graph multiplicity in a mixture model, basically in each cluster, we assume that all of the parameters, they are identical, right? So that means there, if we are doing a mixture model based framework, that's the graph multiplicity for each cluster, and the parameter is just 1 because everybody is the same. Okay, but here when it comes to a spanning tree model, that we basically will have the inverse of this many possible spanning tree. Okay, so that is why we will have this additional term here. Okay, so actually this term is a key that separates us from the existing like spanning tree, like a deterministic spanning tree based algorithm. Okay, because you can see that if we marginalize with this extra term in the posterior, actually this leads us to do clustering based on the well-knitness of a cluster. So here's what I mean. So if you think about having this likelihood in a particular tree, and so we have this inverse multiplicity term here. Okay, so as you can see, in order for this partition, the particular partition to have a high posterior probability value, that means you need to have a lot of different configuration of trees to have a high value in this likelihood. Okay, so here I show you two different examples. So for example, if we only have one particular tree with a large conditional likelihood, but the other possible trees, they all have a small value, then this multiplicity term will give a huge discount. Okay. However, if you have just one tree here, one possible tree here, but you have like some other trees that also give you a high conditional likelihood, you can see that is showing in dashed red here. Then you will be able to get a higher value in the marginal posterior. Okay. So that means just to reiterate, the key difference about accommodating the randomness of the tree is that we get to cluster based on the well-knitness of a cluster. Okay, so before I jump to the theoretical justification, I just want to quickly show you how do we make the posterior computation much simpler. Okay, so far, yeah, go ahead.
So when you said well-knit, the previous slide, what do you mean by that? Like it's not just Euclidean distance.
So what I mean is that the number of this conditional likelihood the number of trees having a high conditional likelihood. So I mean, so you have a lot of different trees that correspond to the same partition that all have like a high value of this. In that case, I call it as a well-knit cluster. Okay. Yeah, I will show you on a numerical example just to show the difference. Okay. So on the computation, we can take this top-down approach to assign a prior like this, but you can see that there is a lot of combinatorial search that we have to do. And or we could take a different approach by assigning this prior using the product partition model. And the nice thing about that is that we can choose the cohesion function to cancel out the terms. And at the end of the day, we will end up with this very simple marginal prior for the spanning forest that is proportional to lambda to the number of cluster. So essentially, this is a truncated geometric distribution. Okay, so let me talk about the algorithm. As you can see, we can imagine a Gibbs sampler that iteratively sampled from the hyperparameter in this tree and then sampling the spanning forest. Okay, and you can imagine it'll be a combinatorial combinatorial hell. Okay, because we need to decide the number of clusters, and then we do node partition, and we need to pick a root, and then you need to sample the edges. Okay, so this is a discrete space and subject to combinatorial constraints. So, but in my opinion, this is where the fun is, because there is a huge challenge. If we can solve that challenge, that just give us immense pleasure of solving the problem. Okay, so we came out with this very neat trick that bypasses all of those combinatorial search. Okay, so here's how it goes. So imagine that you have these nodes, and we can imagine that there is an auxiliary node that we call 0, and we connect this node 0 to those two roots. As you can see, by connecting this disjoint spanning tree, we get a Wilbur tree that is a single tree that connects everybody. Okay, so that means we can, instead of doing all of this, we can just sample this enclosing tree, and then at the end of the day, when we collect all the posterior sample, we just simply cut off the edges connect to node 0. Okay, so as you can see, this automatically take care of the partitioning, including the number of cluster, because like the number of cluster is just equal to the number of edges connecting to this auxiliary node 0. Okay, so there is this beautiful probabilist paper by Aldos in the 1990s, tell you how do you sample a spanning tree. Okay, so it's a really cool algorithm. So this is something called random walk covering. So basically, if you think about a weight matrix, you do random walk on this matrix, and then it is shown that this will produce a distribution for this particular enclosing spanning tree. Okay, so that means that the algorithm can run really efficiently, and I encourage you to try it out. And we have it on GitHub, and it's just a coding in vanilla R, so it's not even like C++ or something. And you can see that the algorithm runs super fast, and the mixing is really good. Okay. Okay, so let me take a deeper dive and to show you the connection to the normalized spectral clustering algorithm. Okay, so just to give a quick review on the normalized spectral clustering algorithm. Basically, if you think about, you have a group of data and you can build up a pairwise similarity matrix, and then you can use this object called graph Laplacian. That is basically take the degree of the adjacency, I mean the similarity adjacency matrix, and then you want to normalize that by taking the negative 1/2 power on both sides, and then you do eigen decomposition on this normalized Laplacian. Okay, and then taking the first k eigenvectors, and then you do k-means on that. Okay, seems very algorithmic, right? And but it turns out this is a very nice continuous relaxation to the following optimization problem. That is, if we think about this thing called the normalized cut loss, that is, if we are forced to divide a graph into k many parts, that's their loss is that because of division, we will have to lose some edges, like between any of those two subgraphs, right? And then I can just adjust this by the number of degrees in each of the subgraph, and I will get this thing called the minimal normalized cut. Okay, and it turns out that because you can see that this happens on the discrete space, but however, you can see that each of this z is basically subject to this z, basically subject to this also orthogonal constraint. Okay, so you can see that we have minimized this. We want to minimize this. This is equivalent to find the first few eigenvectors, and then you can discretize it as corresponds to a continuous and then discretized approximation. Okay, so as you can see, this is basically the normalized spectral clustering algorithm. Okay, so let's change perspective a little bit. If we start with a Bayesian spanning Fourier model, and we want to come out with an approximate estimate for the posterior mode. Okay, assuming that k is known, what should we do? Okay, one thing we can do is that we can look at the marginal probability of each potential edge that is being covered by a tree. Okay, and you can look, you can see here we denoted by this this matrix M, and as you can see, when I and J is covered by a component spanning tree, it must be in the same cluster. Okay, so that means this M is a lower bound estimate for the code assignment probability. Okay, so in order to get to the posterior mode, you can see that we come up with, we will end up with this a maximization problem. And the very nice thing about this is that this M matrix, although it is a probability, marginal probability of the spanning tree, and it turns out that this M matrix has a closed form. Okay, this is due to the Kirchhoff's tree matrix tree theorem, and we can compute this matrix in closed form. Okay, so as you can see, we have two matrices to compare. One is this NA normalized Laplacian, and one is this marginal connecting probability matrix. And this picture shows you the, at least empirical comparison shows you the first few eigenvectors and the largest few eigenvectors of this marginal connecting probability matrix. They look almost the same, right? And so this actually was our starting point, because we look at this eigenvector, we were like, hey, they look almost the same, and then we just dig deeper, and then we found out this connection. Okay, and not just only empirical evidence, but we found out that this two set of eigenvectors, they are provably close to each other. Okay, and the gist of the proof is that you can write this M matrix as a perturbation form of this negative of the normalized Laplacian, and then you can basically just characterize the eigenvector differences via Davis-Keehan theorem. Okay. All right. So just to summarize the potential benefits of the theoretical finding is that first of all, you can see that now the normalized spectral clustering algorithm basically just gives an approximate posterior mode for the Bayesian spanning forest model. Okay, and then second of all, now since we have a generative model, we can do principal uncertainty quantification, and now it is very easy to do model-based extension. Okay, so just to follow up the discussion with Anirban, this shows you when we just use one spanning tree and we do cutting, you can see that if you get a spanning tree connecting everybody and they want to cut the longest edge, you will end up, I mean, we would end up with like a singleton here, and then the bulk is here. Okay. However, if we try our best and just sample a lot of trees, and then we look at the marginal probability of the partition, you get to see that we will have a cut like this. Okay. So as you can see, we will have much less sensitivity there. Okay, just to quickly show you some numerical results. And for example, we could cluster data from Gaussian mixture, and certainly I would not pretend that our model always works the best, especially when you have the component kernel that is correctly specified. You can see that the for example, the Dirichlet process mixture, Dirichlet process Gaussian mixture models, they work really well. But what I want to show you is that our model, even though being flexible, that means that sometimes we may capture everybody as being just in only one cluster. But if you look at the mode of the posterior distribution, we still get to capture the correct number of a cluster. Okay. So just as a disclaimer, it remains an open conjecture on the theory on recovering the number of a cluster if we have model generated from a spanning forest. I think it's a very interesting point of study for future work. Okay, and let me just skip over the T mixture, and I want to show you that when you have a data that not necessarily comes from some distribution that has a clear concentration, we will still be able to capture the clusters. Okay, because what we essentially model is basically the pairwise relationship from one data point to another in the same cluster. Okay, so as you can see, this is very flexible. I mean, in the practical performance, the model tends to be very adaptive. Okay, so to show you a model-based clustering, I want to talk about this existing idea that I empirically played with, and it worked really well. This was proposed by René Vidal from Johns Hopkins. So this is an idea called the subspace subspace clustering algorithm. Okay, so the essential idea behind this is that the data themselves are expressive, meaning that you can think about one data point and you can reconstruct this data point using several other data points in the same cluster. Okay, so that is why you can say that this YIEC can be written as a linear combination of several other data points. I should say that J is not equal to I here. Okay, and then perhaps after getting this W, we can what they do is that they use the spectral clustering on this W matrix. I mean, they use this W to construct the similarity matrix. Okay, and from a Bayesian perspective, we can come up with a generative model. And interestingly, this will lead us to something that is very popular in spatial statistics, where they call this thing as a simultaneous autoregressive SAR model. And but the difference is that this W matrix is not known, and it is something that we'll estimate here. Okay, and what we do is that we will assign a spanning forest model on this W, and because if you think about each of this W is essentially a low-dimensional vector embedded in the n-dimensional space. And then what we can do is that we assume that each of this W lives in a low-dimensional sphere. So if you have two data points from two different clusters, they may have this W living two disjoint unisphere. Okay, so we call this W as the forest sparse embedding. And okay, I want to show you the data set. This is something that we pull from Kangol, and it is the Yale face photo data set. And you can see that here shows you the 3 photos of one subject, and this is 3 photos from another subject. You can see that there are a lot of interfering factors. For example, like the brightness is very, I mean, the illumination is very different from these 2 days, right? And it turns out this is a very difficult problem if we apply like the existing approach, such as Gaussian mixture, or even the mixture of Gaussian, assuming that the covariance living near a certain low-dimensional space. Okay, because if you look at the Euclidean distance of the pairwise between data points, you can see that it's very, very noisy. And we try this using k-means, and we get accuracy of about only 18%. And if we use a mixture of a near low rank Gaussian, and the result is still just 30%. However, if we apply the sparse embedding, as I mentioned, based on the forest model, you can see that we get a much clearer signal here, and this shows you the posterior similarity. Okay, you can see that we get a very clear separation from cluster to cluster. Okay. Okay, just to summarize, so to our best knowledge, this finding of connection between the Bayesian spanning forest model and normalized spectral clustering algorithm is new, and we are working on actually using this as a generative model for some of our motivated application. For example, we are currently doing partitioning of the brain region. As you can imagine, one intuitive assumption that we can impose is that a region of a brain should be a connected region. So naturally, this spanning tree idea or a mixture of spanning tree idea will come in very nicely. And we are excited about this because it has been known for a long time that the Laplacian cofactor, meaning that the eigenvalue of the Laplacian has a connection to the spanning tree distribution. But what we found is that it also has a deep connection to the normalized Laplacian and the connection to the eigenvectors, and which are the key objects that people use for clustering. Okay, so potentially we could extend this as a dimension reduction tool. For example, we could have a very flexible extension to the Laplacian eigenmaps. And I also just like reemphasize that we made this code really efficient, and you're encouraged to download it and just try it in your own application. Okay, and that's it. Thank you so much for your attention, and happy to answer any questions you may have.
I think we definitely have plenty of time for the actual question.
So so there are generative models for inner product statistics,
Mhm.
inner product statistics that has connections with spectral.
Mhm.
So is there any connection between what you proposed?
Yeah, right. So certainly you can we can have something like a stochastic block model, and then people have shown that there's a connection between stochastic block model from a certain generative model and then using the spectral clustering algorithm asymptotically. I think that the difference here is that here we do not assume that each cluster, let's say, comes from a Gaussian or from a, let's say, a Bernoulli distribution with a common parameters. Here, what we do is that we just assume that the data points in each cluster, they are dependent. They're dependent to each other. I guess that's the main difference there. Mhm.
Yeah. So you said that the partition is of the main interest and the actual keys they are like nuisance function. So I was wondering how much is your method sensitive to the estimation of the actual key? So I think in your slide 25 you showed that your method is robust to like if there are some model specification errors there. But I was wondering, do you have some more insight or more concrete results on this?
Yes, that's a great question. So, so the fact that this model seems to be somewhat robust is that if you think about it, what we are modeling is kind of like the shortest distance from a data point to several into its neighborhood. So, for example, we could say that you could have a distribution, let's say, generated from a T distribution, maybe not Cauchy, but maybe like a T with relatively small degrees of freedom. You can say that certainly you get a lot of you get a small portion of a data point that is away from the center. But maybe if you look at the bulk of the data inside of under the curve of the T, once you have enough data points, they will be dense enough. You can see that those distances they are relatively small. So of course, there are ways to break this model. So there are always like some possible scenarios that this method may not work. But I think that what we discover, at least in the theoretical connection, is that you can choose any distribution for the root and for the leaf. As long as the conditions are met, then you will get this nice connection to the spectral clustering algorithm. Yeah.
For the base application, what was your objective? Like, what are you clustering for?
Oh yeah, that's a good question. So I should say this is something that we use to benchmark our model. Just so basically this thing was done that pretending that we don't know the identity of the photo. I mean which subject did we take this photo from? So here in this data set we have 10 subjects. So what we did is just basically just combine them together and then do cluster and see if we can correctly allocate each photo to each person. So initially we did this on the MNIST data, like this handwritten digits, but we figure now pretty much everybody is doing MNIST, so let's just try something new. So that's why we end up doing clustering of face photos. Yeah.
So I think you mentioned the appearance of the term in K to the power NK type term.
Can you say that again? Sorry, I can.
So in the likelihood formulation, you had terms like weighted terms like, but the weights look like NK to the power NK.
Mm-hmm.
So and you say that appearance of that term. So
Okay.
differentiates a lot of the differentiates your method from a lot of the existing methods. Can you point towards the key advantages that you gathered from appearance of that term?
Oh, appearance of that term. So I guess yeah. I get your point. So you can think about. Is there a marker that I can use? You can think about the other extreme. What if we only have one cluster? I mean, what if we have two manifolds? For example, like this, like two crescent moon manifold, and you have data. Oh, I don't know if you can see this. Let me just scroll bigger. Okay. Okay. So if you, oh, okay, that one doesn't work. Okay. So let me just make this thicker. Okay. So if you can imagine, like, if you have two manifolds that look like this, you have data generated from here. Okay. So when we have something like this, I call this actually like a not well needed. This is like a bad needed cluster because I mean, this is like, I mean, each cluster is not well neat because you can imagine that there probably are not many highly probable trees that are connecting those. Okay, so that means when you have some noise here, okay, should you conclude that there are two clusters or one cluster? And being Bayesian, what we are able to see is that we don't know for sure. Okay, so there is a probability, there is a high probability that this, what data tells me is that there is just one cluster. Okay, however, if you think about having more data points, for example, you have more like around here. Okay, and you have more like here, then you can see that there are different ways to form spanning tree with a high conditional likelihood here. And probably, hopefully, that you have higher percentage of data points near those two manifolds as opposed to the ones in the middle. So in that case, this is where you get to see that our model will have a higher discriminability in telling that there are two clusters as opposed to one. So I hope this somewhat addressed your question. Mm-hmm.
I have a simple clarification question. So when you run a deep sample, do you actually sample graph itself or set new instance for your modular deep sample? We do sample the spanning trees, but it's just that this algorithm can run very efficiently. So we can just easily get let's say we can easily get like 1,000 or 10,000 iteration very quickly. So so after we're getting all of those trees, we just look at each tree and we extract the partition. And then using that, I mean, for example, you could look at as a pairwise close clustering event, and you will take an average. You will be able to get the posterior similarity matrix.
Yeah. So as a follow-up, I really like your deep sample. So I was thinking that if we run some really naive M70 sample for the spanning tree problem, and we still use your model, then can I say that one major issue is that because of that MK to the MK minus one constants, then it's very easy for those naive samplers to get stuck. But for your sampler, because you design that before the move, you think that's really no.
Yeah. Okay.
Improve the mixing
Yeah. So one reason that we get like a very good mixing is that if we are keeping the hyperparameter, like those scale parameters in the Gaussian and in the Cauchy, if we keep those fixed and you sample the spanning tree, it's actually not MCMC. It's just independent Monte Carlo. So that's why that we, I guess, just intuitively speaking, that's why we get like a really mixing in terms of like the partition here. I guess a lot of this is attributed to the probabilistic findings during the 90s on how to sample spanning tree. On the other hand, we explore the alternative of doing a Gibbs sampler by moving one edge at a time. I think in a paper that we call Bayesian spanning tree about 2 years ago, there we consider that if you have a spanning tree likelihood that may not be decomposable over the edges, things will get messier. So that you can think about, you have a spanning tree. How do I change this spanning tree into another? Perhaps one idea is that we can remove one of the edges and place it somewhere else. And we also came up with a nice Gibbs sampler. And empirically speaking, that one is computationally more expensive per iteration, but somehow the mixing seems very, very good. So I guess that could be like a potential point of study. Yeah, thank you for your question. Yeah.
That's a very nice question. So under your generative model, how would you describe the cluster? So if your generating model was correct, what would be the description of clusters under that?
Description of cluster. So there will be the data point generated from the same component tree. So I will consider that as one cluster.
But then you are also marginalizing over that. So
yeah, right. Okay, let me rephrase. I guess one explanation on the generative process is that you can imagine that if you have several data points as a cluster, you can first draw one of the tree, and then based on this tree, then you generate all the data points in that cluster. And there might be some uncertainties on these, on which tree that the data generator picked in the first place. Mm-hmm.
So would it then be possible to get an idea on, like, get a prior distribution on the number of clusters?
Right. So right now we put a discrete prior on the number of clusters. Yeah, and it seems to work empirically on recovering the ground truth. But when it comes to theory, we encounter some difficulties because the data points, they are no longer IID. So we cannot apply dupe theorem. Yeah, we have some other work in trying to correct the behavior of a Dirichlet process mixture model, and we will be able to prove that we can consistently recover the number of clusters, but not in this case because the data are not IID. So I guess that's a very interesting challenge. Yeah.
Any more questions? If not, let's thank Leo again for.
Thank you.